Hey everyone, today we're talking about carbon dating. So, the first page of today's notes is a reading section, which we've never had before, but it actually explains what carbon dating is. And then we have three examples because really it's the same type of problems that we learned yesterday. Once you understand what carbon dating is, I think it makes more sense to do the problems that way. So this says a child mummy is discovered high in the Andes Mountain, and archaeologists would like to know when the child died to determine the age of its civilization in this remote location. Well, how do scientists know how old an object or human remains are? What methods do they use, and how do these methods work? So basically, this first paragraph explains what happens. Okay. So it says cosmic rays are highly energetic atomic nuclei or other particles traveling through space at a speed approaching that of light, with some having traveled for billions of years. These cosmic rays enter the Earth's atmosphere in large numbers every day. For example, every person is hit by about 500,000 cosmic rays every hour. It is not uncommon for a cosmic ray to collide with an atom in the atmosphere, creating a secondary cosmic ray in the form of an energetic neutron for these energetic neutrons to collide with nitrogen atoms. When the neutron collides, a nitrogen-14 atom turns into a carbon-14 atom and a hydrogen atom. Carbon-14 is radioactive and has a half-life of about 5,730 years. So, as soon as a living organism dies, it stops taking in new carbon. The ratio of carbon-12 to carbon-14 at the moment of death is the same as every other living thing. But the radioactive carbon-14 decays and it's not replaced. The carbon-14 decays exponentially with its half-life of 5,730 years, while the amount of the stable carbon-12 remains constant in the sample. By looking at the ratio of the carbon-12 to the carbon-14 in the sample and comparing it to the ratio of a living organism, it's possible to determine the age of the formerly living plant or animal fairly precisely. Because carbon-14 has a relatively short half-life, so we're saying that almost 6,000 years is short, it can come undetectable fairly quickly. This procedure is only accurate for dating formerly living organisms up to 50,000 years old. Because of this, other radioactive isotopes with longer half-lives can be used to date older fossils. So, for example, potassium-40 has a half-life of 1.3 billion years, so that can be used to carbon date, aka find the age of something that is obviously well over 50,000 years old. Okay, so let's get started on an example. It says, it can be determined that a mummy found in the Andes contains 77% of its original carbon-14. If the half-life of carbon-14 is 5,730 years, how old is the mummy? So if you recall from yesterday, this sentence, or part of a sentence right here, if the half-life of carbon-14 is 5,730 years, that's enough information to get a rate at which carbon-14 decays. Then we can figure out how old is the mummy, okay? So we're going to start by writing an equation and solving for the rate given the half-life is 5,730 years. So once again, we don't know the original amount, but we do know we're using the PERT model. So times E2, though, we don't know what the rate is, but we know that the time is 5,730 years. We also don't know our final amount, but we know that half, or 0.5, is left. 0.5 of that original. Okay. All right. So now I have to solve for R just like we did yesterday. So I want to use logs as a reminder, but I have to get this by itself in order to log both sides. I need to get the base and the exponent. So I'm going to divide both sides by A naught. Those cancel. Now I have 0.5 is equal to E to the 5730 times R. Now I can log both sides. I'm going to use natural log since the base is E. Remember, that'll make sure my exponent comes in front, so I'm going to go ahead and write that in front. Natural log of E is 1, and then to get R by itself, I'm going to divide both sides by 5,730. This will give me my rate at which the carbon-14 decays. So I put this in my calculator. Remember, this isn't my final answer, so I'm going to store this as X. If you put it in your calculator properly, you should have negative 1.20968, and then there's an E on the end with a negative 4. This is just so that you can check. You're going to store this as X. Okay, now we're ready to answer the actual question they're asking. It says, it can be determined that a mummy found in the Andes contains 77% of its original carbon-14. So it doesn't have 50%, it has 77%. How old is the mummy? So we're solving for T. We're looking for its age. All right, so once again, I don't know why I put a dot right there. I don't know the original amount, but I know that it has 77% of the original amount of carbon-14 remaining, times e to the, my rate is stored in my calculator, times, and I'm solving for T, right? So this is stored as X. So if you want to call that X instead, there's absolutely no problem with it as long as you realize that X is what's stored in your calculator. Okay, I'm solving for T, which is an exponent. So I'm going to try to log both sides, but I can't do that until the base and the exponent's by itself. So first, I'm going to divide both sides by A naught. I have 0.77 equals E to the rate times time. Natural log both sides. Natural log of E is 1. And then remember, R is stored in your calculator and you're trying to solve for T. So I'm going to divide both sides by R, which is just your stored X value. So in my calculator, I'm hitting natural log of 0.77. If a parentheses opened on your calculator after natural log, make sure you close it and then divide it by your stored X value. We are going to round our answers to the nearest thousandth. So you should get 2160.609 years old. Please make sure you have your calculator out and you are practicing getting these answers also. All right, let's try another example. A fossil containing 41 milligrams of carbon-14. Given the half-life of carbon-14 is 5,730 years, determine the age of the fossil if it originally contained 80 milligrams of carbon-14. All right, so once again, I need to find the rate for carbon-14. So I have A naught times E to the, I'm looking for the rate. The time is 5730, but I know that I have half of it left. Now, if you look, this is the exact same equation, the exact same work right here. So you do not have to do it again if it's carbon-14 again. So I'm just going to say my stored X value. Okay, so now I can go ahead and answer the follow-up question. All right, so you have a fossil contains 41 milligrams of carbon-14, and it is determined that the age of determine the age of the fossil if it originally contained 80 milligrams of carbon-14. So I know it originally had 80 and it now has 41. So that's almost half. Keeping in mind that this is almost half, I know that the answer is going to be pretty close to 5,730 years, but a little bit less than that because it's almost half. It's not quite half. Times E to the, my stored rate, and I'm looking for time. All right, so once again, I'm solving for T time right here. First thing I need to do is divide both sides by 80. If you put this in your calculator, you do get a nice decimal. You can leave it as a fraction if you want, though. Natural log both sides. Natural log of E is 1. And then once again, I'm solving for T, so I'm going to divide both sides by R, which is my stored X value. So if you're using X instead, that's absolutely fine. Once again, we thought about this answer before we even put it in our calculator. We know that it's going to be pretty close to 5,730 years because it's almost half left. Should get 5,525.875 years old. Okay, last problem. If you want to pause the video and try this one yourself and then come back and see if you got the right answer, I think that's a good idea. All right, so this one says, suppose a saber-toothed tiger contains 20 milligrams of carbon-14 at the time of death. Approximately how much carbon-14 is present in its remains 30,000 years after it died? So first off, we have to find the rate at which carbon-14 decays. So once again, that's my stored X value. That's the rate that we have stored, okay? All right, so now I can answer this question. It says, a saber-toothed tiger contains 20 milligrams of carbon-14 at the time of its death. So that's our initial amount. Approximately how much carbon-14 is present in its remains 30,000 years after it died. So we have E times our stored rate, and then we want to know how much is left after 30,000 years. So we're looking for a final amount right here. So this is probably the easiest one. You just put this in your calculator, right? Because those are all knowns. What you're solving for is A. So in my calculator, I'm typing 20 e to the, my stored X value times 30,000. You can round to the nearest thousandth. If you think about this logically here, the rate that carbon-14 decays is 5,720 years. So after 5,720 years, there'll be half, which is 10. And then if you double that, which is close to 12,000 years, it'll be half, which is 5, and then half. And you keep going until you're about close to 30,000. So the answer should make sense that it's around 0.531, and then this was in milligrams. Okay, so when you're working on your homework, from what I recall from last year, the first problem asked you about carbon dating and using carbon-14. And then I think the next few do also. So if you want to say I'm using my stored X value at each problem instead of redoing the work to find the rate every single time, that's absolutely fine. Just don't forget how to find the rate, because if we change up the isotope that we're using for carbon dating, we want to make sure that you can